Today's lesson is on topic 2.3, which is about work, energy, and power. Hopefully much of this is a review from last year. So again, we're going to be talking about kinetic energy, gravitational potential energy, and elastic potential energy. Three topics that we talked about, we understand and have used the formulas. Hopefully you still remember them. But on the new side, we're going to be looking at work and power as energy transfer or rate of energy transfer. Anytime we see rate of something, that's going to imply that we're going to be looking at a derivative, or in this case, we're going to be looking at the amount of work transferred over a period of time. Certainly we'll look at conservation of energy, and a topic that we didn't really talk much about last year, but we will touch on it this year, is efficiency. If we look at what we're going to be covering and applications and skills, it should be important to note that we're going to be looking at force distance graphs. Okay, so again, anytime we have a graph, we have to remind ourselves, what does the slope of this graph mean? What does the area under the curve mean? In this case, the area under the curve of a force distance graph is going to be the force times the distance, or the work that is being done in a situation. We'll also be looking at the various formulas. We should be familiar with them. Note that we're definitely going to be using the cosine form of this. Even under guidance, it says, we're not going to be parallel. So therefore, the cosine of theta is going to be important, where work is the force times the distance times the cosine of the angle between those two. And we'll talk about what that means from a math point of view. We have a new formula here in terms of efficiency. It's basically just a number from 0 to 100. You can be 100% efficient. Not likely, as a system that is 100% efficient would imply kind of perpetual motion machine, which is not a possibility. We'll also be looking at force distance graphs as shown here when force is not constant. Okay. So, in physics, energy comes in many different forms. We're going to be working with the various forms on the left-hand side. We don't really touch that much on the chemical, biological aspects of energy. But we will definitely be talking about kinetic and potential energy. And topic 3, we'll touch on thermal. We have the nuclear, solar, and sound energy. All of these different kinds of energy we will be looking at some point. So first off, kinetic energy. This is the energy of motion, or as I like to call it, useful energy. For something useful to be done, something must move. And so we have the energy of motion. Kinetic energy formula is 1/2 mv squared. The right side of that is the formula that IB uses. And because the v, yes, it's a vector, it can have a positive magnitude or a negative magnitude indicating a velocity in the negative direction. But as long as I'm squaring it, it's going to end up as a positive number. So kinetic energy is always positive. There is no concept that belongs with a kinetic energy that's negative. This motion can be macroscopic or even microscopic. Up till now, we've basically been focused on just macroscopic, large objects or visible objects that are moving. Okay, as we move later into various units, in particular the thermal unit, which is coming up in a fairly short amount of time, we're going to be looking at the individual kinetic energy of the molecules. I kind of alluded to this when we talked about systems and said we don't look at the individual atoms. Well, at some point we will. Potential energy exists in different forms, okay? We have gravitational, elastic, and electric potential energy. We all talked about those last year. But in all of these situations, there has to be some external force or some force being applied to the object that prevents that potential energy from being converted into kinetic energy. If I lift an object, okay, my hand is holding it in the air. As soon as I let go of it, that gravitational potential energy gets converted into kinetic energy. Same with a spring. If I stretch a spring and I release it, it quickly tries to return back to its original length. Or electric potential energy. All of this requires some external force preventing it from being transformed into kinetic energy. So looking at gravitational potential energy, when we're talking close to the surface of the Earth, and this is what we looked at last year, the gravitational field is pretty much constant, 9.8 meters per second straight downward, per second squared downwards. And so we end up with this formula that says gravitational potential energy is just the mass of the object times g, that 9.81, times delta h, where delta h is the change in height of the object. Okay, frequently we define an arbitrary zero level, usually the lowest point in the picture, but it doesn't have to be that point. As we look into gravitational distances, which we will in Unit 6 and Unit 9, gravitational potential energy changes because g is no longer this constant of 9.81. Instead, it takes on this form of minus capital G, where capital G is the universal gravitational constant, 6.67 times 10 to the minus 11, m1, the mass of object 1, times the mass of object 2, divided by the distance separating them. If this formula looks familiar, it's not exactly what you're familiar with, because they're probably thinking of Newton's universal law of gravitation, which has gmm over r squared. But that's for the force between two planetary objects. Okay. Instead, the potential energy only has a single r, so this formula is correct. Couple of points on potential energy. First off, unlike kinetic energy, potential energy can be negative. There are a couple of reasons for this. Okay. The first reason is that my potential energy here, the delta H, that's based on an arbitrary zero level. If I define my zero level to be the top of the Empire State Building, everything at the street level is going to have a large negative potential energy, which means for me to get to the top of the Empire State Building, I have to actually add energy. Okay, the elevator needs to take me up. On the other hand, if I define my zero level to be the street level, it doesn't take any energy to drop something from the top of the Empire State Building and have it come all the way down. Gravity does all the work there for you. The second reason, if I look at the second formula here, okay, this is a negative formula. All of the variables there are going to be positive values, so my gravitational potential energy is always going to be negative. But in this case, all the negative sign indicates is that the force that's creating that potential energy happens to be attractive. Okay, that's all the negative sign indicates. And if one object was released, it would then be attracted to the other object. If that potential energy became positive, as you would have in the case of two positive charges, or two negative charges in the case of electrical potential energy, then that force is repulsive and the objects would move away from each other at that point. Elastic potential energy is the energy stored with springs. We have Hooke's law down on the bottom that says the force of a spring is going to be equal to minus K delta X, or the amount as a spring is stretched or compressed. The minus in this instance implies that the force is opposite the direction of displacement. We'll see more of this when we talk about simple harmonic motion in waves. And this formula of the force of a spring is actually not in topic 2.3. It's in a later unit. But the elastic potential energy is in this unit, and it says that the elastic potential energy is going to be 1/2 K delta X squared. Okay, so again, it's the amount that the spring is stretched or compressed. A lot of times people just use the actual length of the spring. Watch out for that trap, okay? It's the change from its unstretched length. Which brings us to work, okay? Last year we thought of work as force times distance, or in some rare cases, we had the force being applied at some angle over the displacement, okay? This year, especially if you've had pre-calc already, okay, you've gone through vectors, and you have to understand that this formula is actually a dot product, okay? Force is a vector, displacement is a vector. What we're doing here is we're taking the dot product of these two values, Okay, so force is at an angle, displacement is at an angle. When we take a dot product, what we're looking at is the amount of that first vector, in this case force, that is parallel to displacement. Okay, when I turn it into a formula form, I end up with this formula that says work is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Okay, and remember, this is the small angle, not the big angle that going the long way around. Okay, so just look at the small angle. We're also going to be focusing on the difference between net work, okay, where all the forces acting on an object is equivalent to the net force, and then the net work would be the work done by the net force. However, there will be times it makes sense to look at an individual force, because by doing so we can evaluate those individual forces while we measure or calculate what the net work is from acceleration and the net force. So that brings us to the work energy theorem, which we talked about last year. In this case, what it says is that the net work done on an object corresponds to the change in the object's kinetic energy. Okay, I don't like this formula all that much because I don't like the fact of just thinking of the kinetic energy. There are times that it makes more sense to think of the work being done as changing an object's energy. It could be potential energy or kinetic energy, but it's not, I don't want to just focus on the kinetic energy. For instance, if I lift an object, okay, at a constant speed, I'm lifting it against gravity, yes, okay, and I've changed the object's gravitational potential energy by lifting it up. I've not changed its kinetic energy, okay, just its gravitational potential energy. So there, I want you to be able to analyze an individual force that way. Yes, if I look at the net force, okay, my lifting it is not the only force. Gravity is also acting there. Okay, so gravity would cancel out my lifting force and I would have no change in the object's kinetic energy. But from an energy perspective, yes, my gravitational potential energy has changed because of this one force. We're going to be focusing a little bit more on that and when do we create a system and what objects are in my system. Power we also looked at a little bit last year. We understand that power is the work done on a system divided by the amount of time that it's done. If these are constants, that's fine. However, this formula is not in our formula book. It's not in the data booklet. Instead, we have this formula because I can make a substitution for work. Okay, work is the force times the distance times the cosine of theta if my angle is not parallel, if my force and displacement are not parallel. And that brings, with a little bit of manipulation, I end up with power is equal to force times the cosine of the angle between them times velocity. Okay, understand that this is not the formula that we have in the data book, okay? The data book just has the formula in this format, okay? But there is a cosine theta associated with this if my force and my velocity or displacement are not parallel. The last thing we talk about in this unit is efficiency, okay? In most systems, only one or two of the forms of energy are useful. The other forms are considered to be non-useful forms and are basically wasted, okay? If I think of a light bulb, yes, it gives me light, and I'm thankful for the light because now I can read in the dark and watch TV. However, they also generate heat, and especially the old incandescent light bulbs. They get hot, and a lot of times that heat is actually counterproductive. If I'm running my light bulbs at night during the summer, I now have to run air conditioning to cool my house. Not useful energy. Okay, if I'm trying to heat something with that light, as in like an easy bake oven, then it's useful energy. Okay, but what I want to look at in terms of the efficiency is the ratio of that useful energy to how much energy I've put into the system. Or in other words, I can look at the power I've get out, versus how much power I've put in. And this is basically going to be a number from 0 to 100. The closer to 100 it is, the more efficient a system is. One way we use to analyze this efficiency is something called a Sankey diagram. We'll see these again in the thermodynamics unit, but in this case what we're looking at is on the left-hand side is how much energy are we putting in what forms are they, okay? A lot of times we just say input energy. All of this energy comes in. Where does this energy go? Okay, if it's useful, it goes straight through to whatever we're doing with that energy. If it's not useful, it basically goes down, and that's what a Sankey diagram is. Okay, down is basically into the wastebasket. And that's why this picture we have here is a low efficiency system. Okay, bringing us back to the light bulb, the old incandescent light bulb is really only about 10% efficient if I'm just focused on the light energy. Okay, if I put 100 joules in, okay, let's say it's a 100-watt light bulb, then really all I'm getting out of that light bulb is about 10 joules of light energy. The remaining 90 joules is heat, which is why easy bake ovens are actually not too bad. Okay, at that point I'm getting 90% of my efficiency for an easy bake oven. But for light bulbs, it stinks. Okay, and that's why we've actually started phasing out, and it's hard to find incandescent light bulbs now. A little bit more efficient, I have compact fluorescent light bulbs, CFLs. Okay, they're about 75% efficient. They do get warm, but not nearly the hot that incandescent light bulbs get. And then the last iteration of that are LED light bulbs. Okay, that's the most recent incarnation of the light bulb. They are about 90% efficient. So instead of having a 100 joule light bulb, a 100 watt LED light bulb, I can pretty much get away with a 10 watt light bulb for the same amount of light energy I would have gotten out of that incandescent. And so therefore I can save a lot of energy and hopefully save the planet a little bit at a time. Okay, thank you.